Okay, so this is going to be our second class for the semester. We are going to be focusing on the basics of microprocessors. And some of you might have already seen this material in Coco, but for some of you it might be new. In any case, we are going to spend the time today to look at the complete instruction cycle of that any instruction goes through. So a lot of things from Coco. So treat this as review if you have already seen these things. The readings from the 5th edition, Patterson and Hennessy, have been assigned for this lecture, 4.1 to section 4.4. In terms of announcements, you guys have turned in your activity 1 that has been graded and it has been published on Gradescope. The solutions are provided on Piazza. So take a look, and the deadline for regrade requests for activities and homeworks is going to be 2 days. So you have a little bit of time to submit any concerns you may have regarding the grading. Let's begin. Before we go into that, right? I want to have a general discussion for just a few minutes. When you're buying a computer, what are your criteria? What are you thinking of? You're buying a computer, maybe for home or office, whatever the need may be. What are you trying to look at? What are the things you would be interested in knowing about? Processor speed, all right. So processor speed, let me just, price. Okay, so price I'm going to put over here. So if price wasn't an issue, amount of RAM, so you're looking at the RAM storage, so hard disk drive, so that's your secondary storage. There is graphics for all the people who are interested in playing games, GPU, so that's related. Cooling, that's interesting. So you would whether it can run Minecraft, sure. Power consumption or battery life, it was a laptop. Number of cores, okay, so that's like here, right? Number of cores. Number of ports, okay. After that, I think the list keeps on going. Battery size is related to power consumption, right? And then everything that, price is kind of like applies everywhere, right? So it's like, okay, for a given amount of price, you're trying to optimize one or more of these parameters of a computer depending on your needs, right? Now, I'm going to highlight a few that are going to be more important and generally more important than others, right? One is the processor. For example, if you wanted to know how many instructions a computer can finish in a given amount of time, then the processor would dictate that. The speed, the clock rate would dictate that. So that's going to be kind of tightly, it's going to be of interest. That component of a computer is going to be very important as we go through the first few lectures in class 2, 3, 4, because we are going to be moving from microprocessor basics into performance of a computer. The RAM, or the amount of main memory that you have, is also going to be very important, and we'll look into RAM and the concept of hierarchy built-in memories I can even include this, but this is secondary. When we go into after lecture 10, how good it functions, this is sort of power consumption is sort of related to the efficiency of a processor, but battery size isn't. Battery size is simply the amount of battery. But these are the kind of things that we would be looking at in this course. We'll be looking at it in terms of how you can improve the performance overall. Right. So, okay. So let's start with the basic building blocks of a microprocessor, which is going to be registers, right? So you guys have seen RTL, Register Transfer Language, in which you treat buses and the important registers that make up a computer as simply a placeholder for bits, and you can move bits from one place to the other, thereby moving the instructions or the data from one part of the computer to the other part of the computer. So what does a register have? Well, it may have an n-bit input through which you could write in n bits to the register. And we have seen in Coco that register is nothing but a placeholder for bits. In this case, a placeholder for n bits, right? So it's used just for temporary storage. It is not going to be part of your main storage that you have on your computer. Although register contents can be written to memory. Now, when you read the register, the contents of the register, then you are reading n bits at a time, and that's going to make up the data that is outputted by the register. So input happens when you're writing to the register, and when you read, data is going to be moving out. Now, in order to control the data moving in and data moving out, you also have two control signals over here, which, hold up, let me see. It's going on right now. All right, so if you guys can help that student get to the right place, somebody give them the link to join the class. It is on Piazza. Thank you. All right, so you use load and output enable control signals to move data in and out of a register, right? So for example, if you wanted to load things into the register, then you would need to activate the load signal, and that comes from the control unit. And if you wanted to read things from a register, you would have to activate the OE, output enable signal. And you have seen the use of output enable, beginning from when we started looking at the tri-state buffers, right? So we would need output enable to read, load to write. Let me just make that note over here. Load to write into register. And this is output enable to read. And of course, we are doing this n bits at a time. Now we could also have more controls that are going to control how data moves inside the register. If you wanted to look at shift registers, you could have shift controls to move data left, to move data right, or maybe you're not interested in shifting it for a particular operation. You don't want to shift it. Then you do no shift, right? For all of that, you would need shift controls. So this is a shift register in which you can write n bits at a time, you can read n bits at a time, load things, output enable things. So that's controlling the write, controlling the read respectively, and you can also shift things inside that register. Another building block of a microprocessor is essentially the core of the microprocessor, right? This is the ALU, the arithmetic logic unit. This is where all the arithmetic and logic operations are carried out. Now, if you look at a very simple block diagram for an ALU, you have essentially two sides, right? A and B. Both A and B are taking in an n-bit number, maybe a 32-bit number, maybe a 64-bit number, whatever that may be. They are each taking two numbers, A and B. They are performing a specific operation on those two numbers, and then they are giving you a n-bit result. And sometimes the user is also interested in monitoring certain flags. There's also an output of the ALU. The flags could be, when I was adding two numbers, I encountered a carry out. When I was adding two numbers, I had overflow. When I was adding two numbers, I had zero result. When I was adding or subtracting two numbers, I had a negative result. So all those flags are also considered as an output of an ALU. They may be monitored in order to do some subsequent operations. We also have an operation input, right? And these are multiple bits. We are of course going to need more bits than one, right? Like with one bit, we'll just be able to have two operations, but nobody is interested in just doing two operations. We would want to do 64 operations, 128 operations, a lot more operations than just 2 or 3. So what do we need for that? Well, if you want to let the ALU know that you want to do a specific operation through bits, then you would need to have those amount of bits as an input to the ALU. So for example, if you had 3 bits for the opcode, operation code, then you can let the ALU know to perform 8 unique operations. And of course, as the size of your opcode increases, the number of operations that you can ask the ALU to do, provided the hardware requirements are there inside the ALU to do those operations, the number of operations would increase as you increase the number of bits associated with the opcode. ALU is a combinational circuit. There's no feedback. So these two things come in, that goes out. There is no feedback loop. There's no memory involved over here. Another building block of a microprocessor is, or are, buses. And you would need buses to move data or instructions from one place to the other, right? Shared collection of wires for exchanging data, for moving data from one place to the other. And whenever we use buses that are being used by several components inside a computer, we need to have a set of defined rules. For example, one thing that is very, very obvious is when you're writing to a bus, only one person or one entity in a computer should be able to write to a bus. However, when you are reading from a bus, then multiple people can read from a bus. It's very, very intuitive, that particular rule. Now, buses themselves can be classified as data buses. For example, the numbers that you want to add or multiply or divide, that is data. Those data lines are two-way. They are going, for example, to the memory and from the memory, right? So suppose you wanted to bring some data out of the memory so that you can run a particular instruction on them, then you are moving the data from the memory to the ALU. Or if you wanted to, suppose, store the results of an ALU operation to the memory, then you are moving data to the memory, right? So that's why we need those data lines to be two-directional, bidirectional. And here we are using n as our size of the data lines. Another bus type is used for addresses only. That's a one-way line. Why is it a one-way line? Well, the only entity that understands addresses is what? When you think of an address, who talks address? Or who understands address? Memory, right? Memory is addressable, right? That's the only thing that is addressable. So from all the other entities inside a computer, the address lines will be going towards the memory, right? They are only going to go towards the memory. So they are one way, and in this case, we are indicating that the number of bits in each address is capital M. They don't need to be the same. They can be all different. N bits for data, M bits for address. And also, we have seen that, say, for example, if we are using a register or a shift register or an ALU, we have seen that we need control signals from the control unit to the ALU or the registers. For example, we need load, we need output enable, we need opcode, we need flags. All these things are going to and from the control unit. That goes under this category, control lines. And they could be a mix of one or two way lines. In this case, we are using C bits for control lines. Some rules, we have already touched upon this a little bit. Rule 1, only one device can write to a bus. Why? If you allow 2 devices to write or 3 devices to write to a bus at any time, then there will be corruption, right? Nobody knows what is actually written. So you only allow one device or one entity in your computer to write to a bus. However, when you're reading, multiple devices can read the bus at any time. And there usually is a bus protocol that is followed strictly by all devices sharing the bus. So those defined rules are in the form of a protocol that is understood and agreed upon by every entity in your design. Now let's talk about 3 registers sharing a bus. Well, in this case, they are kind of talking with the data bus, right? The n-bit data bus. Although some things we need in this are coming through the control lines. So we have 3 registers here, register 1, 2, and 3. And suppose you wanted to move data from register 1 to register 3, then you would have to activate or inactivate certain control signals in order for that transfer to take place, right? So for example, if you wanted to move content from register 1 to register 3, you would have to first write the contents of register 1 to the data bus. Then you can move the contents of the data bus into the register. So you would have to write to the data bus, then read from the data bus. That's how you move contents from one place to the other. Now, because you're writing to the data bus, we have already seen that we have to have a very strict constraint on writing to a bus, which is only one device can do it at any given time, which means only one of these output enables can be true at any given time. Because when you are doing OE, that means that you are moving data out of the register and on to the bus. You are reading from the register and you are writing to the bus using OE. So only one of these can be active at any given time. However, load means that's the control signal that I'm going to use to write to the register. And where am I writing it from? I'm writing it from the bus, right? So essentially I'm reading from the bus and writing to the register. And there is no rule on reading multiple devices reading from a particular bus, which means multiple of these loads can be active at any given time. The OE, the output enables, are coming from the control lines, and the data itself here and here, for example, is communicated or moved using the data bus. This slide just talks about what we just discussed, right? Like how do you move contents from register 1 to register 3? You make output enable 1 active. That will allow you to write the data or contents of register 1 onto the data bus. Then you have to make load 3 active so that you can read from the bus and write to the register. Now let's focus or move our attention to RAM, right? What are the buses and registers associated with RAM? So when you're thinking of memory, you are probably thinking of 2 things, right? Whenever you think about memory, you think about an address and the contents at that address, right? Like only 2 things. Memory, whenever we are dealing with memory, you deal with address and you also deal with contents at that address. Now, what are the different operations you can do with memory? In general, two of them: write to the memory and read to the memory. And both of these operations, writing and reading, involve these two things. For example, if you are writing something to the memory, you would want to know where to write at using the address and what to write using the contents at that address. Whenever you are reading stuff from memory, you would want to know where are you reading it from, the address, and what did you read? What was the data read from that particular address location? So for both these operations, we need to think about a particular address and the contents at that address. Now, when you think about the address, let me color code this here. Maybe I use a blue. When you think about address, you think about memory address register. When you think about, let me use a different color here. Sure, green. Contents at that address, you think about a memory buffer register or the memory data register. So there are two registers here that are very important as long as any operation is concerned with respect to the random access memory, the RAM. The memory address register and the memory buffer register, also called as the memory data register. What does the memory address register hold? It holds an address of the thing you want to write at. Where do you want to write the data? At that address. So I should load that particular address location in MAR so that the RAM knows which address you are writing to. What do you want to write at that particular address? You need to put the contents to be written at that address into MBR so that those can be written at that particular address location. How about for the read? Well, for the read, you would want to know the address where you are reading. You need to put that address in MAR before you read, before you try to read. And whenever you read the data, after it is read from the RAM, that data moves into MBR. All right. And of course, we need to be able to control the read and write signals that come out from the control unit. So that's there. Memory control signals. The request. Why is that? Because sometimes you may have multiple RAM chips. Which one are you trying to access? That is controlled by the chip select. There is also, of course, the read or write signal. When that particular line is 1, you are reading data from the memory. When that line is 0, you're writing the data to the memory. There's also a wait signal that comes out of the memory. If you're trying to do some writing or reading in a very, very fast manner, then the RAMs ask you to slow down, right? Asks the processor to slow down. And that's the wait signal is used to indicate that to the processor. Questions here about the MAR and the MBR. Memory address register needs to have the address that you are trying to either write to or read from. Memory buffer register or memory data register will have the contents. When you're trying to write, then it'll have the contents that you want to write. When you're trying to read, it'll have the contents after you read that memory location. Okay. Let's ask another question here. We said in our earlier slide that data bus is n bits earlier. And then we said our address lines were m bits. Based on that, what would be the number of bits in MAR and what would be the number of bits in MBR? How many bit register is the memory address register? How many bit register is the memory buffer register? M bits in MAR, that is absolutely correct because it needs to be consistent with the address bus. So addresses over here are M bits. Brilliant. The data, MBR, N bits. Excellent. So those need to be consistent, right? Now let's ask another question here. If M is the number of bits that are used for any address, then how many address locations are present in this particular memory? I'm drawing each horizontal line to indicate each memory location. So how many such memory locations exist in this RAM? 2 raised to m, perfect. I need m bits for 2 raised to m identifiers, right? If I had 3 bits, then I could have 000, 001, 010, and so on, right? I have m bits. That means that my size of my RAM is going to be, at least the vertical size, the number of locations is going to be dependent on the number of bits I have in my address space. Now, how about the width? Let's talk about that. How about the width? How about this guy? How many bits are over here? At each location, at each horizontal location, right? You have something like this, right? How many bits are over here in total? N, right? N. There should be N. So you're essentially storing N bits, capital N bits, at each location, and you have 2 raised to m such locations. You guys see that? All right, let's move on here. Some key concepts to build a computer, and we are going to be focusing on the stored program computer concept. What does that mean, stored program computer concept? That means that everything is in the memory. The instructions are in the memory, the data is in the memory, everything is in the memory. This is an instruction controlled digital system with a memory. Well, we need the memory because that's where everything goes. A sequence of instructions is stored in the memory. So what happens in this idea is that you pick a space in the memory and then you say, all right, I'm going to write my program in a continuous fashion at certain memory addresses. Now, whenever I need to start executing those instructions, all I need to do is point to the first address. After that, it'll keep running one after the other, and it'll go through all the instructions that are written at that particular segment in memory. So sequence of instructions are stored in memory. This set of instructions constitute the program that defines essentially your machine's behavior. The same memory also holds the data. Suppose you were adding 2 numbers. That was the instruction. Where are those 2 numbers? They are also in memory. They don't need to be continuous. They can be at a different location. All we need to worry about is the address to that number or data. So the same memory is holding the data that we need to execute the program. We will see some examples here if this doesn't quite make a lot of sense at this point. The same memory also holds the outputs produced by the program. So for example, if you are adding two numbers and storing the result, that result will be stored in the memory. That applies even for intermediate results. So if you want to hold some intermediate results in memory, you would have to write them to the memory. So in this stored program concept, theoretically, your memory is large, ideally infinite, right? You can write programs, as many programs as you want, indefinitely. The next idea is, what would a complete instruction cycle look like? Now, before I do this, let me play a little game. So I'm going to treat you guys as a computer, right? Like suppose you are a computer. And I'm trying to run certain instructions on the computer. So essentially my goal is to ask you guys to run some functions, to run some operations, to execute certain instructions. So I'm going to do this. My first step is, this is me communicating to you. Do something. What do you guys respond with? So the obvious question is, do what, right? Like you wouldn't say, okay, right? What is that something, right? So your question is, do what? All right, that's understandable. So I'm going to say, do the instructions, or I should say perform the tasks that I have written on this piece of paper. All right, what do you guys respond with? Where is the paper? Can I have the piece of paper? Sure, right. Now, can I assume that if I let you know about the location of the paper, you will be able to carry out the tasks? Can I say that? Well, assuming that I know that in terms of hardware, you guys have the capability to do this. I will write it. You are absolutely right. I don't know if I can read. Sure. So it's my responsibility to format the instructions in a way that you would be able to understand. So it's on me. It's not on you. But in general, I hope you guys agree that at least you will be able to get started with this. Now, I want to zoom out here a little bit and then talk about this. Does this change? Does this cycle change depending on instructions? Is this like a generic cycle for every something that I would want you to do? I can follow this procedure every time, right? I start with, I want you to do something. You say, all right, where? What to do? I say, all right, I've written up in a piece of paper. Then you say, where is the paper? I give you the location of the paper and you're good. I can follow this scheme no matter which instruction I want you guys to do. that will actually help us understand this instruction cycle better, because this is exactly what happens. It's an infinite loop of the same thing going on over and over again, unless the user says, stop doing instructions. I'm going to write a command, write an instruction in the memory which says to the processor, stop, right? Like I don't want you to perform any more instructions, right? That would need to be explicitly mentioned. Until then, it'll keep on going in an infinite loop. So the step number 1 is to fetch the next instruction from memory to a register. The register is usually called the instruction register. What is that? In our example, it was you fetching the piece of paper, right? So the processor will need to fetch the instruction, the next instruction to be executed. It needs to move that from the memory to a special register, which is the instruction register, IR. The instruction register holds the instruction to be executed next. However, so that's like the piece of paper, right? In our example, that's like the piece of paper. However, I had to tell you the location of the piece of paper. And the way I do that is through the program counter. So this is what is on the piece of paper, and the program counter has the location of the piece of paper. So in other words, the address of the next instruction is stored in a register called the program counter. So I say do something, you say do what, right? I say go look in the program counter. When you go look into the program counter, you will find the address to the piece of paper, the address to the next instruction. Where do you need to look at for that? You will need to look at in the memory for that, because even the instruction register is part of the memory. Once you get the instruction register and you decode the instruction, then you will know what to do. What is the task? So after fetching that, you need to get instructions, from the beginning, get the instruction address from the PC, from the program counter, read the instruction from the memory, transfer the instruction to the instruction register. So those 3 steps are essentially, where is the piece of paper? I'm reading the piece of paper now. I know what the piece of paper has. I understand what the piece of paper has. I've decoded the instruction in step 2. Step 3 is, in order to perform this task, I will need some numbers. I need some operands. I need some data. So fetch operands from the memory in order to complete that instruction. After you have the operands, you know what instruction to execute. In step 4, you will execute that instruction. Usually that happens in the ALU, the arithmetic logic unit. Step 5, do internal housekeeping. In other words, go back to step 1. So increment the program counter by 1, right? When you increment the program counter by 1, what happens? You are looking at the next address location in your memory. What does that have? It has the address to the next instruction to be executed. So the cycle keeps going on and on, unless you see a stop or a halt instruction come in. Questions here? Let's talk about a structure of a computer. You have the CPU. the brains of your machine, right? That's your central processing unit, or simply the processor. It has two major parts. One is the control unit and the other is the data path unit. The data path unit is also called the execution unit because it consists of temporary data storage and functional unit. So what are the different parts of a data path unit? Registers, shifters, ALU, buses. All these components fall under the category of data path unit. Whereas the control unit is essentially the mastermind, right? Like that's the finite state machine that is responsible for sending control signals to increment program counter by 1. So it's like the entity that is controlling the puppet, right? And the puppet itself is the data path unit. And between the processor and the memory, you have the addresses, the data that can go either way, or the control signals that can go to the memory. The control signals, these read and write signals, are essentially going from control to memory. The address goes into the memory. The data can move in and out of memory depending on whether you are reading or writing to the memory. So think about it like this. Processor, memory, those are your two main things. The processor broken down into control and data path. Control is your finite state machine that is essentially the entity that is controlling all the other mechanism, right? Like that's your finite state machine that sends out control signals to all the other components in your computer. Whereas data path is the workhorse, right? That's the registers, the ALU, the shifter, the buses. Now let's focus on the data path unit. There's no memory involved in this. So memory is over here. We are not looking at memory right now. We are just focusing on the data path unit. The ALU, the registers, the buses. That's it. This is a single bus design. So we are using one single bus to communicate between all the components in the data path unit. One bus. That puts a limitation, right? Later on, we will be moving to a 3-bus design. PC stands for program counter. This is your piece of paper, right? It holds the address of the next instruction. IR, instruction register. That particular register holds the fetched instruction. That is the instruction to be executed next. AC, accumulator. Accumulator is involved in most instructions. It is the placeholder for intermediate results. Suppose you wanted to add 3 numbers, right? N1 plus N2 plus N3. You can add N1 plus N2 first, store the result in accumulator, and then add N3 to that accumulated result later. So for all the intermediate operations like that, you can use accumulator. And that's why we need the accumulator, right? Because it has, ALU has two entries. One of the outputs of the accumulator is hardwired to the A side of the ALU. And this can help with most of the intermediate storage, right? Like for example, I said N1 plus N2 plus N3, right? When you add N1 plus N2, you move the data back into the accumulator and it is hardwired, right? So it's available on this side already and you can move N3 from there. The bus is your highway to transfer data from one point to the other. Now, if you look at the bus, the program counter, the IR, the accumulator, then there is also the memory buffer register and the memory address register. Where do you suppose everything starts? Like which register over here is where you think everything starts from? The PC. Absolutely right. the program counter is the key. Program counter is where everything starts. Now with this single bus design, we are going to look at all the possible register transfer operations that you can write down, that you can list out for all the things that are in this single bus design. For example, you may want to move the contents of program counter onto the bus, and that's how you would write it. Your PC is anyways the register, but you can also treat the bus as a register. So PC to bus is a pseudocode to indicate that that's the register transfer operation that could take place. That is, let me highlight that in here. PC to bus, where is that? PC to bus, right here. Then you could also have IR to bus, which is right here. Then you could have accumulator to bus, which is right here. And there are many others. You can do memory buffer register to bus, ALU result to bus, which is right here, bus to PC, bus to A, and you guys see what they are. But everything is sharing one bus, right? Like all these are sharing one bus. So if things have to move from one place to the other, then you need to go through the bus. In other words, for all these register transfer operations listed, except for this last one, which is hardwired, bus is one of the things that is involved. Right? Bus. Let us talk about how things would go, right? Let's just talk about that cycle. We agreed that everything starts from PC. Why? Because PC holds the address to the next instruction. So what should be the first register transfer operation that should take place for any instruction? Which one should take place first? No matter what it is, PC to bus. Okay, I agree. All right. So that's one. What next? What's going to be next? Bus to IR? No. So you see, what does PC have? PC has an address. Who understands address? Memory understands address. Right? So it has to be bus to MAR, which is next. Okay. What is going to happen after that? So we have gone from we have done this, right? Like we started here, then we went here, then we went here. We are here right now. What is going to happen next? Are we going to read from memory or write to memory? Read, right? Okay, so we are reading. Why? Because we want to know what the instruction is, right? So we have an address that's holding the address of the next instruction. So we want to read the memory to find out what that instruction is, right? So we read the memory. When you read the memory, what happens then? You know the address where you are reading because that's MAR. So that's what you send to the memory. What is going to happen as a response after the reading? What happens? Bus to MBR, right? Okay. So memory to MBR, right? So that the contents will move from memory to MBR through the memory data bus. So now we have the instruction to be executed in MBR. What happens next? MBR needs to go to what? MBR needs to go to bus, sure. After that, what? Everything, bus to IR. Brilliant. You see what we did? We went from PC to MAR, MAR to memory. We did a read. After we read, the instruction came into MBR. Then through the bus, it went into IR. What did we do? We fetched the next instruction. That's all we did. We just fetched the instruction. Next, we need to decode the instruction so that we can carry out the operation using the accumulator and the ALU. That follows after that. But hopefully this gives you a good idea about how things are going to flow and in which order generally. What does decoding mean? Well, every instruction has an opcode, a limited number of bits that indicate what operation needs to be carried out. So the control unit needs to look at those specific locations for the opcode and then use a decoder to understand what that is and then carry out the corresponding operation, meaning send the corresponding operation signals to the ALU. I'll talk about the construction of the IR, right? The first few bits are opcode and the later bits are operand address. I'll talk about that. All right. Now let's break this up into a 3-bus design. Why? Because this is going to support parallelism. How do you know that? Well, once you have 3 different buses, I can be writing from PC to address bus to MAR, and at the same time I can be moving data from the ALU onto the result bus, right? Now, not that specific example, but I'm just saying that you could be doing multiple things at once because you have more than one bus. So this will increase the number of things that you can do at the same time. That's your parallelism. So single bus being replaced by a memory bus, the result bus, and an address bus. Memory bus is being used along with the memory. This is memory data bus. So memory bus is right here. Then there is the address bus. Talks addresses only. Then there is the result bus. That is going to be dealing with the results of the ALU. What do you think the size of the memory bus is? Using our previous N, M, and C for data, address, and control, memory bus is of the size M bits. Okay, how about the result bus? N. How about the address bus? Oh, memory bus is not. No. Memory bus needs to be N, right? Because you see, memory bus is right there. It is talking to the MBR. So that's data. It is talking to the ALUB side. That's data. That's talking to instruction register. It is not talking to PR. It is just talking to IR, right? So memory bus is N. Result bus is N. The address bus is the only thing that is M, because that's the only thing that is talking address. No problem. All right, let's put everything here. We still did not put the control unit in this diagram, but we have put like almost everything here, at least in terms of the data path unit and the memory. So all these things are sort of the data path unit. And this is of course, your memory. And we talked about y 2 raised to m and y n bits wide. We talked about that earlier in the lecture. So where does everything start? Program counter. So program counter through the address bus moves contents to MAR. From the MAR, you read the instruction at a particular location. You move that to MBR, which is also inside the memory. MBR to IR. Some part of the instruction register may need to go back into PC or may need to go back directly to MAR. In what situation? Let's take a look at this special case. There is a connection between instruction register and PC. For what type of instruction do you think that could be useful for? So instruction register has the instruction to be executed, right? And it has a direct connection to PC, which actually holds the address of the next instruction. So in what type of instruction that could happen? Here is the answer. Branching. Suppose skipping an instruction. Absolutely, yeah. So you are skipping multiple instructions, right? So suppose you are trying to go through a list of instructions in a sequence and you want to branch out, right? Like you want to jump around in your memory. What do? You have an instruction called branch, and part of the instruction itself will be the address to jump to. And when you have that loaded in the program counter, you essentially skip instructions, jump to any instruction, right? So that's called branching. We use that for that. IR also has a connection to MAR. That is used to fetch operands. You want to add two numbers. Those two numbers are in memory. Part of the instruction will be used for the address of the operand. You move that address to MAR and read. When you read, that moves into memory to ALU B side. You guys see that? Now let's put some more things into it. Let's put control unit into it. That's where your control unit is, right? So let's go back into this. So first things to notice with this FSM, the finite state machine, which is your control unit, it is having all the load and output enable signals that go to PC, to MAR, to the operations lines for ALU, for accumulator. Looking at the opcodes inside the instruction register, decoding the instruction happens here. The red lines in this one are for the control flow, essentially your load and output enable and the operations lines for the ALU. The black lines are essentially your data flow lines that we have been talking about. So suppose the instruction was as simple as add two numbers, right? How do you know it was add two numbers? Well, when you got things into the instruction register, the first few bits in the instruction register, which constitute an opcode, was decoded by the FSM, and based on that, it was determined that addition is the operation that we need to do, and the resulting code was sent to the ALU in order to ask it to add. We will go through this sort of cycle again, but I hope you are getting a better picture with every little addition that we are doing here. Let me pause just for a second, see if there are any questions at this time. I'm hoping that as we are doing the examples later on, you guys will get a very good picture about how this is going to go on for every instruction. All right, let's move on to how does this work. So here we are going to trace a load instruction. This should help with the activity today. This is a load instruction. What are we doing? We are loading something into the accumulator. Let's state a load, and the instruction is, so we are just doing a add instruction here. The addition instruction is what we are executing. The instruction is the current contents of the accumulator need to be added to something that is present in the address, and the result of that addition needs to be stored in the accumulator. Again, you have some number in the memory, and I can tell you where that number is by providing you the address. The number that I want you to add, there are two numbers, right? One number is already in the accumulator. The second number is in the memory, some address in the memory. So if I tell you the instruction and I give you this address, you should be able to do it. The instruction is add to the accumulator. And what do you do with the result? You store the result back into the accumulator. That's the instruction that we are going to go through. Where does everything start? It starts with fetching the instruction, right? Because when I said do something, you guys said what? And you said, okay, I need to look at the piece of paper, right? So you went to look for the piece of paper. So we need to do instruction first, instruction fetch first. That is going to be our first step in every instruction cycle. So we move the contents of PC to MAR first. What am I skipping here? I'm skipping micro operations. What are micro operations? Micro operations are move contents from PC to a bus, then to MAR. I am skipping that micro operation in the middle. I'm just writing move PC to MAR instead. Now, once I do move PC to MAR, I need to initiate a memory read sequence. That is like trying to read the piece of paper. When you initiate the memory read sequence, the data from the memory will move to the memory buffer register and then eventually move to the instruction register. Once the instruction to be executed is in the instruction register, we have completed the instruction fetch phase. The second one will be instruction decode. Look at the instruction register. What does it comprise of? Well, two things. There is an opcode and there is an operand specifier or operand address. The opcode will let us know to add or to branch or to halt or to multiply, to divide, whatever, or floating point arithmetic, whatever that might be, the opcode is going to tell us that. First few bits in the instruction register. And what follows is the operand address. In this case, it will be the address that we want to, the address to our second number. That will need to go there. The second step, coming back to the instruction decode phase. The finite state machine, which is our control unit, is going to take a look at the opcode bits and try to decode what operation needs to be performed right now by the ALU. Once it decodes that, it will send control signals to the ALU to let it know, okay, this is the operation that you're doing right now. Operand bits of the IR are the input to the FSM. The rest of the IR bits are for the operand address. The next step is the operand fetch. Why? This second number is in the memory. I need to do addition in the ALU, which means I need to bring that particular second number from the memory to the ALU B side so that I can do the addition, right? So I need to do operand fetch. I've given it the address right here. My address is given. I just need to go to that address, read that address, move it through the load path to the ALU B side. So Operand fetch involves move of operand address from IR to MAR, initiate a memory read. Remember I said earlier that this is going to be our fetch operands line. That's exactly what we are using here. We are using this particular line. Oh, sorry, not here, right here. That particular line to do the operand fetch. We also need to initiate the memory read sequence because the data that we are reading, which is essentially this number here, is going to go move from the memory to MBR through the load path, and it will be ready over here on the ALU B side. The fourth step, instruction execute. What are we doing in instruction execute? We have the data available on the ALU B side. The accumulator data was already hardwired to the ALU A side. We knew that we were adding, so we need to just configure the ALU to perform the add operation and then move the result from the ALU result side to the accumulator. Why don't we go through PC for 3? Hold on. Oh, because you see, this is an address of operand. PC holds address of next instruction to be executed. So one is a address of instruction, one is the address of operand. All right, let's come back and do this. All right, then we move result from the ALU result to the accumulator, that completes that instruction. Housekeeping means update the program counter so that it points to the next instruction. Essentially means PC plus 1. Increment the program counter by 1. For this, you don't need to use the ALU. You can use the ALU to do this, but since this is housekeeping, there is an automated version already implemented in your computers to do this very commonly performed housekeeping instruction. Okay. What is the control unit doing? Well, it is transferring data from one register to the other, asserting the appropriate control signals. What are the examples? Load, output enable. We can think about the control unit as easily in terms of register transfers and micro operations, and we are going to use a programming like notation. What is that notation? It is the register transfer notation. The language itself, which is symbolic, is the RTL, the register transfer language. A way to represent detailed implementation of the register transfer operations. And we will be talking about the RTL, register transfer notation, for this lecture. Sometimes you don't need to explicitly mention the micro operations. For example, when you say PC to MAR, right, we have kind of skipped the micro operation of PC to bus to MAR, right? We have skipped the micro operation of moving to the bus in the middle. So micro operations go down to each and every detail. Those are detailed operations. Okay, let's take a look at, this is again load accumulator A. Hold up, what is this? What is the instruction here? It is doing addition. So we are again doing AC, right? Yeah, AC plus address. So things like this, those are address locations. Things like this, those are registers. The whole thing itself is the register transfer notation. So we have five steps in our cycle. Fetch, decode, operand fetch, instruction execution, and then housekeeping. those 5 steps remain the same for all instructions. So for example, where does everything start? Everything starts at program counter. So when you do this, program counter moves to MAR. Then you initiate the memory read sequence. Memory contents will move to IR. That completes instruction fetch. Then you take a look at the instruction register, specifically the opcode bits. If they match the opcode for add from memory, then you go on ahead, right? So here you see this, you are comparing the opcode that is currently in the instruction register to a lookup table. Who gives us the lookup table? The programmer, right? The programmer writes up a manual which says, okay, this is the code for add from memory. This is the code for store to memory, right? So all those codes are predetermined, that they are designed. So once you compare the code in the instruction register to a lookup table, if it matches add from memory, then we are going to be doing all these things. What is that? First, operand fetch. We need to take a look at the operand address, which was part of the instruction register, go through the MAR so that we can read it. Once we read it, our the number from the memory is ready on the ALU B side. Then we do the instruction execution. Memory to ALU B, accumulator to ALU A, add, then the result goes back to the accumulator. That's your instruction execution. And as housekeeping, we have PC plus 1 going into PC, increment program counter by 1 so that it points to the next instruction to be executed. If you do not want the next instruction to be executed, then you need to execute a branch instruction. We are going to be looking at 2 examples. One is load a particular address location. Well, I should say load the contents at that location into the accumulator. And we'll go through this in a lot of detail. And the second example which you guys are going to be focusing on in the activity is store the current contents of the accumulator to a particular address location. So these are exactly opposite of each other, right? Load contents at that address to the accumulator. Store the contents of the accumulator to a particular address location. This is our 3-bus design, and we are going to be trying to look at these 2 instructions in detail, all the 5 steps. So what needs to happen when you load a particular address location, the contents of something, load the accumulator with contents that are present in the address location. What needs to happen then, right? So here, let me go back here. The memory is here. The particular address is over here, right? All these are your bits over there. What are we trying to do with this load instruction? We are trying to move this guy to this guy, from here to here. That's the instruction that we are trying to do. In the store example, we need to go back. Not to that same location, but somewhere else. Let's go through these steps. The first step, instruction fetch. What needs to go on? The first thing that we look at is the program counter. Contents of program counter move into the memory address register. Initiate the memory read sequence. Then memory buffer register or memory data register will now have the instruction to be executed. Those contents will need to go into the instruction register. Once that is complete, we have completed the instruction fetch phase. Does this change for store accumulator A? Well, load accumulator A, it has a mnemonic LDAA. That is load accumulator A. If you usually you have two accumulators, A and B. This is just doing a accumulator A. You're loading accumulator A with a certain memory location. Does this change for store? Does this change for store? Would it change? Nope, it doesn't change. The instruction fetch is going to be the same for all the instructions that need to be executed, right? What changes is the second step. In here, when we are trying to do the instruction decode, we are looking at the opcode field in the instruction register, and we are trying to compare that with a lookup table that corresponds to the instruction load from memory. Load accumulator from the memory. If it matches, then we do these things. How would this be different for store? Well, I will compare it to store to memory, right? In the operand fetch step, which is the third step, we said the instruction register has two, instruction register IR has two fields. One is the opcode. Where did we use that? Right here. To compare. The other one is the operand address. Quick question. What is the size of our addresses? In general, we have been looking at some addresses, number of bits in an address, right? So what is this? Oh, in the M, right? So M. How about this? Remember, instruction register needs to be consistent with MBR, and it needs to be consistent with the width of the memory. So what about this? Total width. Total width is n, right? Just n. So how many bits are there for the opcode in general here in our general discussion? N minus m bits. So what is the max number of operations that we can ask the ALU to do? Two raised to n minus m. Perfect. All right, let's come back. So if this field right here, opcode, is being used here for comparison, for decoding, where is that operand address being used? It's being used right here. So this operand address, which is part of the instruction register, will need to move into MAR, memory address register, initiate the memory read sequence so that contents at that particular address, which is the second number, will move to MBR and later move to ALU B side. Instruction execution, which is simply going to be MBR to accumulator. We are not adding here. We are just simply moving things to the accumulator, right? So the instruction, because it is load to the accumulator, right? So once we have, let me go back here. So let's talk about the execution. The execution would be pass through and accumulator. That would be the execution, right? So it's getting loaded from the memory over here. It is passing the ALU nothing happening in the ALU, passing the ALU and going into the accumulator. Doesn't the MBR go into doesn't the MBR go into the memory bus and the AC is connected to the result bus? So here it needs to pass through it just needs to pass through the ALU. Load to ALU, the instruction to the ALU is passed through, goes to the accumulator. Where were we? Right here. So MBR to accumulator, we are clubbing all of that into one. Then we do the housekeeping, which is increment program counter by 1. Now, this is your activity exercise to do store accumulator to a particular memory address that you will do as part of the activity today. I'll just mention that, mention what we are doing. Store current contents of accumulator to memory address given in instruction. Right, so we are given the address, we know what we are moving, AC, so we need to move AC current contents into the memory. Where to write in the memory is address given in the instruction. What to write? AC to write. That are going to change in the store, is the instruction execution. Well, this is going to change, right? Instead of load from memory is going to be stored to memory, and also the right, instruction execution will change. You're right. That's the main thing that will change. Some micro operations that I would like to point out. For example, pass B, we used that, right? When we did the load accumulator, we did a pass B. That is a micro operation, which essentially means whatever you see on the ALU B side, just pass it through to the ALU result. Add, which is essentially increment program counter by 1, or sometimes you might want to initiate the program counter all the way to 0. All of those are considered as micro operations. Now, if you want to take a look at how does a register transfer notation compare with a micro operation, you will see that PC to MAR, it might be one register transfer notation. However, it is a combination of 2 micro operations, which is PC to address bus to MAR. So if you are asked to write all the micro operations, then you are listing out everything in detail. If you are just asked for the RTN, then you are just looking at it from a slightly more like a summarized view. When you're doing a memory read and contents of memory are going into IR, look at the difference. When you say memory read, over here it is an explicit mention. Let me use a different color. Explicit mention that the read signal needs to be 1. Are we going to use both notation? Well, sometimes you're asked this, sometimes you're asked that, right? Like it depends on what the question is going to be. In general, you would stick with RTN unless it is specified otherwise in the question itself. Memory to IR. What is that? MBR to MBus, MBus to IR. You see, each instruction may have one or more than one micro operation involved. The full program of load accumulator with a particular something in the memory is listed over here. This is the full program, which means it has all the micro operations that are there. So quickly, let's run through the 5 steps here. Program counter to address bus to MAR, initiate the memory read sequence, contents of MBR go on to MBus and end up in IR, completing the instruction fetch. Comparing the opcode field of the instruction with load from memory. If that matches, then load the contents of the operand address field into the MAR, initiate read sequence so that the operand can be fetched from memory to the ALU B side, which in other words is MBR to MBus, MBus to ALU B. Let's see if I missed what is the one being loaded. So when you means you got it. All right, so let's see. Where were we? Right, we had the number to be to be loaded in ALU B. Then you do ALU pass B. That means don't do any addition, multiplication in the ALU. Just pass whatever you have on the side B. ALU pass B appears at the ALU result. Move that through the result bus to the accumulator. Increment program counter by 1. So that's for load accumulator with something from memory. What do you know about that something from memory? You know the address of that something from memory. Now you guys are ready to go and attack the activity. It is uploaded on Piazza. It is due tonight. Again, help sessions are available later on in the day. This should not take too much time, but it's due at midnight. I will be here for any question you may have.